In this video, we will take up a problem from torsion. Actually, it involves concepts from, say, torsion, then bending, then say Moore circle, etc. So it's a very good problem taken from the book Mechanics of Materials by Beer and Johnson. So it's quite a nice problem which discusses many of the concepts which are involved in these three topics. So let's concentrate on this problem. So now this problem tells that there is a steel pipe. This is AB is that pipe. It's an hollow pipe. It's not a solid pipe. Having outer dia of 102 millimeters. Okay, outer dia 102 millimeters. Wall thickness is 6 mm. Here it is shown. Yeah. Then there is a arm CD which is attached to the pipe rigidly. Okay, so rigidly it is attached. That means there is no slip between the arm and the pipe. Okay, almost like a welded joint. Now the question asks you to find out the principal stresses. Okay, so there comes the concepts of Moore circle and transformational stresses, etc. And maximum shearing stress at point K. Okay, so there is also a point H which is shown in the picture. We will discuss a bit about that point also towards the end. So let's start discussing about the point K, which the question is asking about. And some other dimensions are also given, and the coordinate system also is shown in the picture. And yeah, so there is a load of 10 kilonewton getting applied at this point C. Now, so how to start thinking about the problem? So that's the most important part. Now, how I would start thinking about this problem is like this. See, this arm is attached, and here there is a force applied, and we are trying to find out the stresses. Basically, I would suppose draw a, a square segment there, suppose. Okay, if you remember, so to define a state of stress at a point, so we should know uh, the stresses on this square, infinitesimal square. Okay, so I could have taken in any orientation this square, but it's obvious that to make this simple, we will take the sides of this square, one parallel to the axis of the cylinder and one parallel to the xz plane. Okay. Now, the state of stress, if we want to show, so we can show that in this square. This is the point K. Fine. So we still don't know. We haven't discussed about what are the stresses which are going to come on this. Let's discuss that. See, now once this force is getting applied here, we know that we can transfer this force to the pipe AB, right? Means, because see, we are not being asked anything related to the arm, so we can simply transfer this force onto the pipe, so that the problem will be simplified and this arm will be gone. So if I do that, but I'll just try to draw the situation. So this will be the pattern. So suppose this is the tube. Okay, and yeah, so let's say this is my z, this is my x, and this is my y-axis. And see, once I transfer this force, obviously the 10 kilonewton force will be acting still in the x direction. Okay, so that's the 10 kilonewton force. But we know that from the concepts of transferring the forces, we will have to have a compensatory um, couple which acts at this. Okay, now that would be how much? It should be equal to the moment which this force was earlier acting at this point, right? So this, that means this is this distance times this 10 kilonewton is the torque which was acting here. So we can show that here like this. So something earlier also was this torque. This force was this had two effects. One, it was trying to bend this pipe, okay, and the other effect was that it was trying to twist it. In fact, for some students, it's easy to or very intuitive to think about the torsion but not about the bending. So be sure that you understand both the things are happening. Now let me see here. I'll write x, y, and z. So this is a torque which is acting at that tube. So that means if you think so the two concepts which are acting, one is bending and the other one is a torsion on the beam. Sorry. Now, if you are finding difficulty to see how these two deformations are acting, so you can split them. Okay, first assume that if you are comfortable with torsion, say, so first assume that this pipe is completely rigid against bending. Okay, so what will happen in that case is if you apply this torque, it will just bend, right? If there was a say line like that, before you apply the torque, it would become something like this, right? So everything will be twisted. So everything will be twisted. But then, so in this case, we are assuming that the effect of this 10 kilonewton is not at all there because it's completely rigid against bending. So this force cannot bend it at all. Okay. So only thing which will happen is what I can do. I can take a copy of this drawing maybe. Um, and put it here. Um, to discuss the other thing. So here we will discuss about say torsion, and there we will discuss about bend. Thanks. Um, so so here I just wanted to draw this thing. If these vertical lines were drawn earlier, so now you will see lines which are like that. So this is the effect of this twist which has been applied. Fine. So this surface will be twisted by some angle phi. But now, what if we assume that this tube is infinitely rigid against torsion? So that means it cannot twist. Okay, but it's somewhat flexible against bending. So then what happens is if you look from this side, it will bend. So I'll just try to draw um, the view as if we are looking from z direction. So the tube will be something like this. Okay, so that's fine. Say this is the y-axis, this is the x-axis, and the z-axis is coming out, okay, of the plane. And then this force is acting in this direction, 10 kilonewton. Fine. Then obviously, and then we have assumed that it cannot twist, so it will obviously, it is fixed here anyways. So then it will bend. Now how the bending will happen? So something like this maybe, right? So this kind of thing will bend. And we are talking about the point at the point K here. So that means in this diagram the point K will be somewhere here. Right? In this diagram the point is here somewhere K. Fine. And in this diagram the point is somewhere here. Fine. So now you can assume because now see, you could imagine both the cases in a split way, the bending and the torsion, but the actual situation is a superimposition of both. Fine. So that means this point is under the action of both the loadings, the bending and the twisting. So that is where the stresses also will come from both the deformation. So now let's calculate both of them separately, and then we can um, add them. Okay, because the principle of superposition works because everything is very small, the deformation, the stresses, so that we are in the linear zone of deformation. Okay, so now let's calculate the shear stress which would be developed on this section. Say, so if I see this square here, so because of the twist, right? Because of the twist, we know that the shear stresses will be developed in this direction, right? So like that. So that we are trying to evaluate how much will be that shear stress. Now that shear stress can be evaluated using the formula that tau max. Why max? Because it is on the surface of the cylinder, and we know that the shear stress due to torsion is maximum at the surface of the cylinder, and which is given by the torque which you apply, the maximum distance from the neutral axis at which this tau max is happening over the polar moment of inertia of the cross section. Okay. For this problem, I'll just write down directly the values. I'll not calculate them here. So now T is given to be how much? This 10 kilonewton times 0.2 meters, right? So that is your what do you call the torque? So it's like so 2000 newtons times 0.2. Fine. Just a minute. Is it how much is that? 200 plus is the it's given from the center only. Yeah, fine. Okay, so it's 1000, right? So 10 kilonewton. So sorry, I should use this. So it's 1000. So 10,000. Should I put 10,000 Newton, 10 kilonewton times 0.2 meters. Okay, so this will be equal to 2000 Newton meter. Fine, so that's the torque. And then the C, C is what? If you look at the cross section, should I draw it? So let me draw it here. If you look at the cross section, fine. Now suppose this point is the point K. We are seeing this as x-axis. Now from here to this distance, right? So there's the farthest fiber is at this location from the neutral axis, because it's axisymmetric. The neutral axis is here. So the maximum diameter, what is the diameter? 102 millimeter dia. So half of that basically. Okay. So C will be equal to say 51 millimeter. So 51 to 10 raised to minus 3 meters. And J you can calculate for the annular circle, and it will come out to be 4.18 into 10 raised to minus 4, I think. Okay, let's say minus 4 meter 4. Fine. Now with these values you can calculate the value for tau max, and it should come out to be, so tau max should come out to be 24, I think 24.37 megapascal. Okay, just check it after you calculate. You should check this. Fine. Now if that's the maximum shear stress, so now you should be in a position to show them on this diagram. So here you have calculated these values. So tau max is now tau max. This tau max is with respect to the torsion. Okay, so that came out to be 24 point. How much was that? 37. Right, megapascal. But so that takes care of the torsion. But then what about the bending? Okay, so there will be one more stress which will come from the bending. So you see here, this side is so if I draw the neutral axis, so it will be somewhere like that. So this portion is under compression and this portion is under tension. So this portion will be under a compressive force from this side and from this side. Fine. So we are now trying to evaluate that stress. So that stress obviously will be, say, sigma y. So that will be you can calculate with the moment which is getting applied. So that moment will be how much? So now this distance is given 150 mm, right? So 150 mm times this 10 kilonewton force. So that's the moment which is applied at this point. So you can think in other way that suppose you are trying to draw the what do you call, the bending moment diagram for this portion of the beam. Fine. So you will see that the bending moment will be 0 here and it will go to a maximum here. Fine. So we are looking at the bending moment at this point. So this value we are looking at, and that will be nothing but the force 10 kilonewton times this distance 150 mm. So that will be m times the maximum the distance of the fiber. So again the value of C and over I. I is the moment of inertia of this annular cross section, okay, about this axis. Okay, suppose this is our ZZ axis, right? ZZ prime. So about ZZ prime, the cross sectional area's moment of inertia is that. Okay, now you will have say this is 1500 times 51 to 10 raised to minus 3, and 51 times 10 raised to minus 3 over the moment of inertia happens to be 2.097 0927, means 27 into 10 raised to minus 6. Okay, so please do check about this number. I'm not very sure of. That will come out to be 36.56 megapascal. Fine. Now if that's the sigma y, we can go and show it over here. So on this diagram, let me take this also to the bottom. Okay. So yeah, so we can put it here. Now we are in a position to put the other, this one. So this is a compressive force, compressive stress, that is sigma y, which is equal to 36.56 megapascal. Fine. And what about this sigma x? Let's say, what about sigma x? Now if you think about sigma x, it's 0. Why it's 0? See, there are no uh, forces which are coming from the bending on these surfaces. Fine, so that's clear. Only thing is, see, there is this force which is acting. So if you also draw the shear force diagram, so this was the bending moment diagram, right? If you draw the shear force diagram, a constant shear is also acting throughout the length of the um, what do you call, the pipe, throughout the length of the pipe. But the thing is, that um, shear stress is acting in this direction. But moreover, what happens is, um, if you see the distribution of this shear stress across the cross section of this annular thing, um, you should know that the distribution of shear stress, and that is going to be 0 at these 2 points. Okay, it will be so something like this, means it will be 0 over here, and it will increase, and then it will decrease. Okay, so something like that will happen. So at both these ends, this is going to be 0. Okay, for a for a completely circular thing, actually the distribution is like that, and the average, if this is the average, and this maximum will be I think 4/3 of this average value. Okay, so but what we are concerned with is these 2 points where the stresses are 0, and that is why actually, we are able to draw this as a plane stress condition, so that only the stresses are acting on 2 plane, x and y. So this is the complete state of stress at the point K. That's the point of concern with us. Okay. So now we are asked also to find out, I think, the principal stress and the maximum shearing stress, right? So once we know the complete state of stress at a point, we know how to evaluate the principal stress and the maximum shear stress. Let's try to draw the Mohr circle and then use the formula using the Mohr circle to evaluate them. Okay, let's try to draw that. Say suppose this is my axis. Okay, this is the sigma axis, this is the tau axis, and let's say we are talking about this plane. So here the sigma x is 0, so that's 0, and on that plane the tau max is 24.37. So let's say this point is that point. So this is, say, it's 0 and 24.37. Then let's draw this plane. This plane is minus 36.5, that is, say, suppose somewhere here, yeah, be somewhere here, minus 36.5 and 24, so yeah, almost like this. So this point, so this is like minus 36.56 and 24.37 point, right? So then if we join these 2 points, we should get the center of the Mohr circle, and then using this radius we can actually draw the circle. Fine. So sorry about that. Yeah, it's not too great, but yeah, I'm not happy with it. Sorry. Yeah, let it be like that. Fine. So we are now concerned with which points? So these are the points. So this is one of the point where the principal stress is existing because the shear stress is 0, and this point at the top, right? So these are the points which we want to evaluate. Either you can draw this Mohr circle to scale and measure them from the diagram, or else you can actually calculate them using the formula. How to get that? So this point is the sigma average, right? So let's calculate that. So sigma average will be what? So sigma x plus sigma y over 2. So that's this and this. Fine. So that will come out to be how much? It's minus 18.28 megapascal. Okay, you calculate, it will come out to be this. So this is that point. So yeah, but then we can also calculate now the radius, right? So this is the radius. To calculate the radius, what you should use, suppose this is, you drop it here, so this distance, let me say this distance is what, sigma x minus sigma y by 2, and this is your tau xy, right? Tau xy. So and we are trying to evaluate this r. Fine. So this is the radius which you are trying to evaluate now. So then r should be equal to sigma x minus sigma y. Sigma x is 0, sigma y is minus 36.56 by 2, square it, then plus tau xy squared under root. So this will come out to be 30.46, it seems. Okay, megapascal. Once you evaluate sigma average and R, obviously it's very easy to evaluate them. So say suppose this is sigma max and this is sigma min. So sigma max, one of the principal stresses, is equal to sigma average plus the radius R, which will come out to be plus 12.18 megapascal, and sigma min will come out to be sigma average minus R, which will come out to be minus 48.7 megapascal. Sorry. Okay. And what about the tau max? So now tau max, which is this point. Tau max is just the radius. Fine. That will be equal to this. So 30.46 megapascal. So these are the three values which we were asked for the point K. Okay, so it became a quite long video because there were a lot of concepts involved, and I thought I should explain these concepts of torsion plus bending completely, even though the video becomes a bit longer. So thank you for watching. So we will solve another problem in the next video. Thank you.